Let us understand the response of single degree of freedom systems. In a single degree of freedom system, we have this generalized spring mass system with a damper. If we draw the free body diagram of this system, we assume that the mass is moving in the positive u direction and calculate the forces that would be acting on it. So in this case, we would have force due to inertia, force due to spring, and force due to the damper acting opposite to the direction of displacement. Taking the summation of forces in the x direction equal to 0, we have the equation of motion like this. We substitute the forces as we know, and we get mass into acceleration plus damping coefficient into velocity plus spring coefficient into displacement equal to 0. We divide the equation by m for deriving the formulations that we need. Here we know that damping coefficient by critical damping coefficient is the damping ratio, from which we derive that C by m is equal to 2 zeta omega. Also from the definition of angular frequency, we know omega is equal to under root k by m. We substitute these facts in our equation and we obtain the solution of such a second order differential equation is given by u of t is equal to g into e raised to st, where g is any arbitrary constant. It should be understood here from equation 1 that u dot and u double dot are kind of linearly dependent, and hence we have our general solution also of the form that makes u dot and u double dot dependent on each other. That is, u dot is g times of u of t, s times of u of t, and u double dot is s square times of u of t. We substitute these in equation 1 and we obtain this expression. We take s into e raised to st, we take g into e raised to st as a common term outside. For this equation to be true at all instants of time, the bracket inside must be equal to 0. We see that this equation is a quadratic equation in S. Hence, we solve for S using the quadratic formula. We substitute the values and finally obtain S is equal to minus zeta omega plus minus omega under root zeta square minus 1, where omega is the natural frequency and zeta is the damping ratio. We define omega under root 1 minus zeta square as damped natural frequency or pseudo natural frequency. Hence we obtain S1 and S2, that are the two roots of our equation. We substitute the values of S1 and S2 in the general solution. As we have two roots, we will have the general solution as g1 e raised to s1t plus g2 e raised to s2t. We substitute the values, we expand the expression, and we know for a fact that e raised to I theta is equal to cos theta plus I sin theta, which can be derived from Taylor series. So hence we substitute e raised to I omega d times of t as cos omega dt plus I sin omega dt. We then isolate the terms of cos omega dt and sin omega dt. At this stage, there is something called as G1 and G2 being the complex conjugates of each other, due to which we only have the real part of it by the addition and subtraction of it. But even if that is kept aside, we may say that G1 plus G2 can be called another arbitrary constant A, and G1 minus G2 times I is B. We substitute it and have this equation. Now this equation is the equation of the response of a damped or dissipative system. We can find the values of A and B by applying the boundary conditions. The boundary conditions tell us that at time t equal to 0, u of t is equal to u0. From this, we find A is equal to u at time t equal to 0. We may also find the velocity u dot of t and similarly substitute u dot of t equal to u dot of 0 at t equal to 0 and obtain the value of B. We substitute these into our equation to obtain the final equation of the response of our system. With this knowledge, now let us move on to deriving the response of a dissipative system when a force is acting on it. We start by the equation of motion by drawing the FBD and divide the whole equation by m to obtain the equation that is shown. The force that is acting is assumed to be P naught sine omega bar of t, where omega bar is the forcing frequency. The force function could also have been taken as a cosine wave. We have the total response of such a system as the complementary solution plus the particular solution. In this case, because there is a forcing function acting on the system, we will have the particular solution. The complementary solution is the free response of such a dissipative system, which we have already calculated before. Particular solution of such a system is of the form G1 cos omega bar t plus G2 sin omega bar t, where G1 and G2 are arbitrary constants. We calculate the velocity by differentiating the equation. We calculate the acceleration by again differentiating, and then we substitute the up of t, velocity and acceleration in the equation of motion that we found out. So upon substitution, we find the equation becomes next we isolate the cos terms and sin terms. Upon comparing the left hand side and right hand side, we find that cos omega bar t and the expression in bracket is equal to 0, whereas there is a sine term on the right side which will be equal to the sine term on the left hand side. Here we have now two equations and two unknowns. Those are G1 and G2. Hence we can calculate G1 and G2. We define a term beta as frequency ratio, that is equal to forcing angular frequency divided by natural frequency. We find G1 and G2 by solving those two equations in terms of beta, and G1 is equal to the expression shown, G2 is the expression that is written here. Moving on, we know that the whole solution, whole response of the system is going to be the complementary part plus the particular part. We have the complementary part from the previous derivation that we'll substitute, and the particular part is of the form G1 cos omega bar t plus G2 sin omega bar t. Let's substitute the values of G1 and G2 and let's bring back the complementary solution. We have this equation. Here we know G1, G2. The only unknowns here are A and B, which can again be determined by applying the boundary conditions. After applying the boundary conditions, we find A and B as the expressions that are written here. From this derivation, now we have done all the cases, that is, for free response we'll be able to calculate free damped and free undamped response, and for the case of forced responses we'll again be able to calculate damped and undamped responses just from this one equation. Let's see how we can do that. So let's start by finding the equation for free undamped response. So if we have a free response, that means our forcing term will be equal to 0. And if we have an undamped system, our damping ratio will be equal to 0. Also, we won't have a damped natural frequency, we would have natural frequency omega n. As we know, omega d is equal to omega n times of under root of 1 minus zeta square. So here if we have zeta, that is damping ratio, equal to 0, then we have omega d is equal to omega n. If we substitute this in the equation that we just found, we'll have A is equal to u naught, because p naught is 0 and hence that whole term will become 0, and we'll have b is equal to u dot naught zeta is 0, so the second term will be 0, and in place of omega d we'll have omega n. And as it is not a forced response system, we'll only have the complementary solution part. So if we just see the complementary solution part, which was u of t is equal to e raised to minus zeta omega t in bracket a cos omega dt plus b sin omega dt. We just substituted the values of p naught, zeta and omega d in the above expression and found out that a comes out to be u naught and b comes out to be u dot naught by omega or omega n. I am using omega and omega n interchangeably, so don't be confused. And here again I'll put zeta is equal to 0 and I'll have this whole e term equal to 1. Anything raised to 0 is 1. Hence we have u of t is equal to u naught cos omega t. As we won't have omega d, we'll only have the natural frequency, plus b sin omega t, which is precisely the equation of response for a free undamped system. Let's say we want to find free damped response. So it is free, that means P naught is equal to 0. It is damped, that means zeta exists. And it is damped means omega d also exists. So with the same procedure, we try to find out A and B. P naught is equal to 0, so we'll only have U naught term. And in case of B, I didn't bring the whole equation for B. So the whole equation for B was with this additional term. So P naught would again go back to 0 and we would get B is equal to U dot naught plus U naught omega zeta by omega d. As it is a case of free response, we will again have only the complementary solution. We substitute the found out A and B values in this and we get U of t is equal to e raised to minus zeta omega t U naught cos omega dt plus U dot naught plus U naught omega zeta by omega d sine omega dt, which is exactly the equation of response for a free damped vibration case. Similarly, we have found out the expression for forced damped case. For forced undamped case, we again found it out by using the complementary solution. So this expression here was the response for free damped situation. We have not found it out for forced undamped situation. So again, for forced undamped situation, we'll have some P naught, but as it is undamped, we won't have zeta and we won't have omega d. Instead, we would have omega n. So we substitute these values in place of A and B and again try to find out. So wherever zeta is seen, I will simply put zeta is equal to 0. And hence I obtain A is equal to U naught and B is equal to P naught by K into omega by omega d is equal to 1 in this case. Minus beta 1 minus beta square divided by 1 minus beta square plus U dot naught by omega. 1 minus beta square and 1 minus beta square would get cancelled. In the equation here, we do have 1 minus beta square whole square, I believe. Let me check. Yes, on deriving we have 1 minus beta square whole square here. We tried to keep the denominator same so that it is easier to compare both the equations. The above equations, that is the case of free damped and free undamped, would remain unchanged because of this, because we didn't have these terms as P naught was equal to 0. But in this case we do have that term, and so I'll be putting square here. So hence we get A is equal to U naught and B is equal to P naught by K minus beta by 1 minus beta square plus U dot naught by omega. As it is a forced undamped situation, it will also have particular solution. So from the constants g1 and g2, let us find out what would be the value in this case. So g1 would become 0 because our damping ratio is 0, and g2 would become P naught by K in bracket 1 upon 1 minus beta square. If we substitute all these values in our generalized equation, that is u of t is equal to e raised to minus zeta omega t a cos omega dt plus b sin omega dt plus g1 cos omega bar t plus g2 sin omega bar t, we get the equation e raised to minus 0 is equal to 1, so we'll have 1 in its place. In place of a, we'll substitute the a that we found out here, which is u naught, u of 0 cos omega d. We cannot say omega d because in this case it is forced undamped system. So omega d is equal to omega n times of t plus b is what we found out here, plus b into sine omega n t plus g1 is 0 as we found out, and g2 is p naught by k in bracket 1 by 1 minus beta square, which is exactly the equation for forced undamped system. So from that one equation we have found out all the equations. Let me just write down what all we have found out. So first we started from free undamped equation, we then found out free damped equation, so we then found out free damped equation, and then we found out forced undamped equation, and before this we derived all of this from the forced damped equation. Sometimes you may also find the expressions for, let's say, free undamped equation to be written as u of t is equal to u naught cos omega t minus theta. where u naught is the amplitude of motion and cos omega t minus theta is the cosine wave that it will move in. So u naught can easily be obtained from under root a square plus b square, the constants that we just found out. In case of free damped equation, you may see the equation written as u naught e raised to minus zeta omega t cos omega dt minus theta, where again u naught can be found out as under root of a square plus b square. U naught is also defined as ust naught into rd, where ust naught is the static displacement and rd is defined as the dynamic amplification factor. So ust naught is given by the static displacement, that is force by stiffness p naught by k, and rd is given by 1 upon 1 minus beta square.